Okay, folks, let me make sure one thing before we get going. As you've probably noticed, there's a slight change here, and that is because there was some kind of issue. I spent a long time trying to identify it, actually, but I didn't have any luck. But there was some issue with using FaceTime and then Tegrity at the same time, or even FaceTime and trying to record something at the same time. So I've moved to Skype, and let's see how this works. The video looks a lot better. I like that, and hopefully the sound will be better too. So let's pick up here with problem 10. This will be the end of the homework from 2.1. And this is a problem where we have three parts. We're going to let A be an integer, and we want to show that each of these things implies the other. Now this is one of these deals where you assume one and show that that implies this one, then assume this one, show it implies this one, assume this one, show it implies this one, and that way they're all equivalent. So I'm going to start with my proof. I'm going to go actually, instead of going from A to B, I want to go from A to C, and my reason for that is this is a little detail that I glossed over in one of the other proofs where we said, okay, if A is odd, then A plus 1 over 2 is an integer. Well, I'm going to prove that now. Okay, so let's start by letting A be odd. Now what we mean by that then is that I should have said then, excuse me. Then there exists some, I don't know, K. That's an integer. Such that A is 2K plus 1. And now what we want to do is consider this thing right here. So A plus 1 over 2 would be 2K plus 1, that's the A, plus 1 over 2. And so this is 2K plus 2 over 2, and I can factor out a 2 in the top and 2 in the bottom, and I'm left with K plus 1, which is most definitely an integer. Thus, A plus 1 over 2 is an integer. Okay, so that was the first part. It's quite easy, and that's why I glossed over so much kind of the first one, because it was pretty trivial. All right, now let's take C and show that that implies B. Okay, so in this one, let's let it be an integer. Okay, so let A plus 1 over 2 be an integer. Then there exists, stick with K. K, that's an integer. That's actually equal to this. So A plus 1 over 2 would equal K. And then I think just to prove B, and you can pause here if you want to figure it out for yourself, but what I would do in this case is solve for A and then consider 3A plus 1. So let's do that. So then A, multiply both sides by 2, is 2K minus 1. Consider 3A plus 1. Well, okay, that's 3. 2K minus 1 plus 1. So this is 6K minus 3 plus 1, 6K minus 2, and you can factor a 2 out of all of that, right? You're left with 3K minus 1 inside. Since 3K minus 1 is an integer, then 3A plus 1 is even. And that's got C to B taken care of. The last step in this is, okay, let's let 3A plus 1 be even and show that that implies that A is odd. Okay, so our last step here is B to A. Okay, so we'll let 3A plus 1 be even. Now what we would typically do in a situation like this is what we've done up above. We would say, okay, then there exists a K such that 3A plus 1 is 2K, right? And then solve for A. But the problem with doing that, and you may do this and figure it out that there's a little issue here, is that you're going to divide by 3. And there's no guarantee from what you're looking at that you're that you've got this magic two integer plus 1 that gives you an odd number, right? So this might actually be a case where you would want to do a small proof by contradiction. Okay, let's suppose for a moment that A is even. Okay, instead. Now I think when you think about this, you'll realize that that can't be the case. If A were even, 3 times the even number would be even, plus 1 would be odd, right? So what we're doing here is forcing a contradiction. So let's let A be even. And now we kind of run our game plan. Then there exists some K that in the integers such that A is 2K. All right. But then when I look at 3A plus 1, that means that I've got 3 times this 2K, which is A, plus 1. And really what I've got is 2 times 3K plus 1, right? And 3K is an integer. Then 3A plus 1 is odd. But that is a contradiction. We said that 3A plus 1 was even. That means that this was a bad assumption. Okay? So since we've done the all the way around, this actually proves the statements are equivalent. Just one final statement to kind of say that. Therefore, the statements are equivalent. There we go. Okay. Hopefully that's working. Hopefully audio is working a little better on this one. And I realize that I've got some lighting issues, some shadows. I don't know exactly what to do with that. I tried to use my phone as a light. That didn't work. But I'll work on that. I still think this is better than using the iPad as a tablet. All right. So, okay, moving on to problem 11. This is where we let m and n be integers and then show that these things are equivalent. That m squared minus n squared is even implies, and the second statement is m minus n is even, and then m squared plus n squared is even. Okay? So it really doesn't matter where you start with this, but we do want to do this thing where we go from 1 to 1 to 1. So maybe I start with just do it A to B. I guess that's fine. Okay. So, and this is where you might want to stop and see if you could do this part yourself, and then come back and check and see what we're doing. So I'll give you that chance to stop right here. Okay. Letting A imply B, that means that we want to let m squared minus n squared be even. Okay. Now, that means that, well, we could do a couple things. We could say that, you know, there exists an integer so that this thing is equal to 2k, you know, integer k, so that this is 2k. But the problem is that you're dealing with n squared and m squared. Really, we want to get this down to m minus n, which is actually a factor of this. Okay, and that's probably the thing that I would point out. I would note that m squared minus n squared is equal to m plus n times m minus n. Okay? Now, this might be a good place for us to, again, do a contradiction. Let's say that m minus n is odd. Okay? Then I think what's going to happen here is that you're going to be able to kind of show that this whole thing would have to be odd as well. Okay, so let's do that. Let's suppose okay, then that means that there exists, we can do the k business now, an integer k such that m minus n is 2k. Okay? And then, all right, so let's say, can we, yeah, I think we can do this. Okay, so, okay. Oh, that's odd. Oh, I'm sorry. That's what was throwing me. It's like, wait, that's not going to work out. But it will if we make it odd, which is what we said. All right, so here we go. Now I'm doing it right. All right. So then, what does that tell us about m plus n? Okay. Well, first it tells us about m. It tells us that this is 2k plus n equal, oh, plus, excuse me, plus 1. Okay. Then consider m plus n. Okay, well, m is this, 2k plus n plus 1, and then plus the n that we have there. So this is actually 2k plus 2n plus 1. And since we can factor that 2 out, this is 2 times k plus n plus 1. Okay. Yeah, I was doing this in my head, like, wait, that's not how it works. But yeah, it does. Okay. So, all right. Then, since k plus n is an integer, then m plus n is also odd. Okay? But if you have an odd number times an odd number, you do not get an even number, right? There's no factor 2 here, there's no factor 2 here. So you don't get a factor of 2. So in the product. So, and I'm just going to say that. I mean, we could actually spend time proving that, but I think that's probably enough for this. This is a contradiction. Since the product of two odds is also odd, and we were told that it's even. So then, our original supposition that that was odd was wrong. Thus, m minus n is even. Okay, and that was the A implies B part. All right, now let's go to B implying C. I think this is a little more straightforward because going from n and m and then dealing with m squared and n squared is actually a little bit easier. Okay, so now we will let m minus n be even. That means there's some k out there such as this is equal to 2k, then there exists a k integer such that m minus n is 2k. And then that means that m is 2k plus n. Now, what I'd like to do is consider m squared plus n squared. And I know that m is this, 2k plus n, quantity squared, and then plus n squared. So what is this? This is 4k squared plus 4kn plus n squared plus n squared. So a bunch of things there divisible by 2, right? I got 4k squared, 4kn, and 2n squared, which I can factor 2 out, give me the 2k squared plus 2kn plus n squared. And since that is an integer, and that means that m squared plus n squared is even. Okay? And then the last step of this process, we have C take us back to A. Here's the C implying A part. Let's let m squared plus n squared be even. And again, we're going from square terms to square terms, so I think we can just solve for one of these. We have to establish that, if there's some k out there, then there exists a k in the integers such that m squared plus n squared is 2k, right? And then that means that m squared is 2k minus n squared, right? Now consider what we're trying to show over here, the A, m squared minus n squared. Okay, well that's 2k minus n squared minus n squared, which is 2k minus 2n squared. A couple things there divisible by 2, right? So factor that 2 out. And since k minus n squared is an integer, then n squared minus n squared is even. And we are, then one last step then saying, therefore, the statements are equivalent. Okay. All right. Hope that helps. Our next problem here is we skipped one, went to 13. Where we want to prove that the sum of a rational number and an irrational number is irrational. Now, when you think about this one, you know, we start talking about irrational numbers. We don't have a good way to represent irrational numbers. So it's sometimes good when we're asked to prove things about irrationals that we turn it around and talk about rationals and use rational numbers to prove things about the irrationals, okay? And that's exactly what I'm going to do here. Turn this into a, there's really a couple ways. I mean, you could do a proof by contradiction. It might make more sense in this case to just look at the contrapositive of the statement, okay? We're looking at a rational and irrational, so let me call the rational number A. Let A be a rational number. And what does that mean? Well, it means that I've got integers P and Q, or M and N, whatever, so that I can write this as a fraction. And there exists, how about M and N? Whatever the denominator is, got to make sure it's not 0. So A is equal to M over N. Okay. Then the statement to be proven is if B, that's my irrational number, is irrational, then A plus B is irrational. Okay? What I say is, let's consider the contrapositive. If A plus B is rational, not irrational, right? Then B is rational. Okay? And that way we can represent these numbers. Okay, so let's let A plus B be rational. And that means that there's some, I can't use M and N, they're in play. Let me get something else. P and Q. In the integers, Q not equal to 0, such that A plus B is P over Q. Okay. And what I want to do is look now at B. Then B is equal to P over Q minus A, but remember, A is M over N. And if you get a common denominator here, this is Pn minus MQ. Okay? Both of those, both the numerator and the denominator, are integers. Qn, because both of them are non-zero, would have to be non-zero. That's an integer. Oops, wrong one. So Qn is an integer. And Qn is not equal to 0. then B is a rational number. And then the last thing to say is since the contrapositive holds, the original statement holds. Okay? See how we turn that around? Another thing you could have done there is you could have said, okay, let's assume that the sum of this number and the other one is rational. The sum of this rational and this irrational is rational, which again gives you the opportunity to go in here with your P and Q, right? And then you could show that B is actually rational, which is a contradiction. Okay, so that equivalent way of doing it with a proof by contradiction. Okay, one last problem in this set, and that was almost a linear algebra kind of problem. Immediately, what I thought of is like, well, you could do a rank argument, but no, let's not. Let's just work it out. You're asked to prove that there is no quadratic polynomial ax squared plus bx plus c, where a is non-zero. That keeps it quadratic. With these four things being true. P of a negative 1 being 2, P of 0 being 1, P of 1 being 3, and P of 2 being 10. Okay? I think this is just a straightforward proof. Okay? We let P of x be this. Okay? And all right, well, if P of 0 equals 1, then that means if we plug a 0 into this, we get 0 plus 0 C equals 1. Okay. And probably put the other two together. I just did that because it locks in. It was easy to solve for just the C. Maybe use the next two here to solve for A and B. So if P of a negative 1 equals 2 and P of 1 is 3, then that means, let's plug a negative 1 into this, A to the negative 1 squared plus B to times a negative 1 plus 1, that's the C. That's going to be 2. And plugging a 1 in there, you get A 1 squared plus B times 1 plus C, which is 1, is 3. Okay? Then what does that tell us? We got A minus B, take that 1 to the other side, equals 1. And A plus B equals 2. And so what you can do is actually add these two things, right? You get 2A, add the left-hand side, you get 2A and 0B. You know, this is the process of elimination, right, for solving systems. 2A equals 3, and that means A is 3/2. Then that means, and maybe put it right here, that we got 3/2 plus B equals 2, or B is just a 1/2. Now consider P of 2. And note that if we look at P of 2, we've got A and B and C all set in stone now, right? So we got the 3/2 for A times the 2 squared, and then plus the 1/2 times the 2 plus the 1. So what is this? This is 3/2 times 4, and those 2's cancel, so that's a 1 plus a 1. Once and twice, so this is 6 plus 1, which is 8, which is not equal to 10. So it just can't happen, right? And that's all we had to show. Okay, I hope this works better. I hope the sound works better. I'm going to take the time to listen to it before I continue on. In the test that I did on it, worked a lot better actually. And I like the visual too. It's got the, I don't know if you noticed on the FaceTime thing, I had like a little box down here, which was a nuisance. So I think this is probably working better, but we will see. We will see. In the meantime, enjoy the video, and I will tape another one here soon.